All right, so now that we've covered a ton of detail about the actual process of mining, the math, the challenge that all these miners are repeating over and over and over at these ridiculous rates. Now we're gonna keep talking about mining in the next couple videos, but we're now viewing it from a distance. We're not talking about how it works up close. We're talking about the competition between miners, who wins what, how it's decided who wins, what happens if there's a disagreement or two miners find workable nonces and solve the puzzle at the same time. All sorts of things that have to do with mining that aren't actually about the challenge itself or the math. So let's start by talking about, or reviewing, I guess in this case, the block rewards that miners receive for correctly solving that puzzle.
So in 2009, for the first Bitcoin block mined, Satoshi, or whoever that is, earned 50 Bitcoin for that block. And the intention was that the block reward would be cut in half every approximately 4 years. So there is a schedule based on the block number. In 2012, the reward was cut in half to 25. In 2016, the reward was cut in half again to 12.5. And at block 630,000, which is projected to happen in 2021, the block reward will again be cut in half to 6.25. Right. It's projected to be, the prediction will probably be quite accurate because every 2016 blocks, the network will adjust its difficulty and thus its target and the rate at which it might mints new blocks. So 2021 is probably a pretty accurate estimate. And a lot of people ask here, why is it being cut in half? And why will miners retain an incentive to continue devoting this much electricity to it? And the thinking is that over time, the transaction fees will come to support miners. So we're going to talk about transaction fees soon, but right now we're just focusing on the actual quantities and how they are awarded to an individual miner.
So back on the Block Explorer, this was the most recent block a couple minutes ago. It may have changed, but what I want to show you is that if you look here, there we go, block reward 12.5 Bitcoin, and it tells you the current US dollars, $114,658 as of recording. Of course, that will change. If we go way back though, let's go to block like 200,000. Is that the right number of zeros?
2 million.
Now you can see 50 Bitcoin for the block reward. And then somewhere in the middle there, it changed to 25. We don't have to go hunt it down. But you'd notice that if you go back and you explore different blocks over time, you'll see that the block reward at some point shifts.
Suppose I'm a miner and I've won a block. How do I actually get the Bitcoin? How do I get this 12.5 Bitcoin? So pictured here is our colorful block diagram. And the top 6 squares, rectangles, are the block header, and the colorful envelopes are the actual transactions. So as a miner, what I'm actually doing is I'm greedily adding a special transaction at the beginning of that list. And that's, in this case, a 12.5 Bitcoin transaction to myself. So this 12.5 Bitcoin transaction is included in the actual overall fingerprint of the block. And what that means is every miner has their own transaction at the beginning of that list of transactions. So, for example, in this picture, we have 2 miners, miner A and miner B. And they each have their own deposit address for any Bitcoin that they would hypothetically earn from mining a block. So pictured here on the left is miner A with the Bitcoin transaction to address A. And on the right is miner B with the similar transaction, but with a different address. And what that means is both miners are mining virtually the same transactions with the exception of this first one.
Right.
So their fingerprints, even with the same nonce, would be totally different. So this first transaction is actually called a generation transaction, and it has no source, it just has a destination. And this is included in this miner's block, and if the miner does mine valid proof of work, then they broadcast the exact block that they've mined proof of work on. And this helps other miners to verify exactly the order and content of the underlying block, not just the headers.
Okay, so here's a little diagram of, imagine we have miner A and miner B. They both are mining away on the same transactions, but they both have optimistically inserted that the generation transaction, the transaction basically saying, I win 12.5 Bitcoin. So all miners are doing that. It's just only one of them is actually going to win it and have that transaction cemented into the blockchain. But they all optimistically think that they are or hope that they are.
Yeah, so that transaction exists on every miner. It just doesn't become real. It doesn't become trustworthy Bitcoin until proof of work is found on that block.
Right.
So suppose miner A strikes proof of work. Then they're going to broadcast that information to the rest of the network. And everybody's still mining. But when they hear that miner A has found proof of work on this block, this one where known as 66 and the fingerprinted little tiger, then miner B is going to see that and immediately want to abandon it and jump in front of miner A's block. Now, why would they do that? And this is an important part of Bitcoin mining. In the Bitcoin network, the longest chain is the most valuable. So miners don't have any economic or personal interest in continuing to mine in a contest for a block that they've already lost. That block will very quickly become irrelevant. And why is that? It's because the entire network switches over to it. And as the entire network switches over, the chain gets longer, and people, users of the Bitcoin network, see the longest chain as the one that is most secure, the one that has had most work applied to it.
So now what I want to do is go back to the Blockchain Explorer, and what I want to show is that not only can we see the reward, so in this case, what are we looking at? Block 200,000.
So back in 2012.
The reward, 50 Bitcoin was only worth $624 back then.
So were they like $12 each back then?
So whoever it was won 50 Bitcoin, around $624 at the time. And we can actually see, if we scroll down here, that generation transaction, which is just the transaction of the miner optimistically adding in 50 Bitcoin to me, or to the miner, to their address, or to an address that's generated for them. You can see it here at the very top. So all these other ones have a from address and then a to address.
Oh my word, look at how big the transaction, 100 to 95.
Yeah, 195, there we go.
Rolling
It was
back
only
then.
$2,000 back then. Today, yeah.
Those people would be millionaires.
Okay, so here we go. They all have a from address except this very first transaction. No inputs, newly generated coins going to this address. So this is the address that whoever mined this, or whatever computer mined this, inserted this transaction and then hashed everything together.
And you'll also see it's 50.63. That 0.63 on top is including transaction fees. So remember, we'll discuss that soon. But for mining a block, you not only get the generation transaction, the block reward, you also get all fees associated with the transactions that you include in it.
And now if we look at a more recent block, we're looking at a 12.5 Bitcoin reward, which currently is worth $100 and something thousand. And you can see here at the very beginning, here's that generation transaction, no from address, and it's to this address of the miner. This time it's for 12.9 Bitcoin, which is 12.5 for the reward, plus the fees associated with this block that the miner mined. All right, welcome back. So in this video, we're talking about orphan blocks. And that's just the name for what happens when you have a blockchain that diverges, there's a disagreement, or two different miners find valid proof of work. One is eventually abandoned, becoming an orphan block. So we'll talk about that process. So here's an example of where it could happen.
Yeah, so pictured here is a scenario where two different proofs of work have been found at about the same time.
Our proof of work here means finding a yellow emoji.
Yeah. So we showed these here and also noted that the contents of the blocks are different in this picture because they can be different. In general, they'd probably be pretty close to one another.
It might just be they've received transactions in a different order, that sort of thing.
Or that they, for example, haven't seen all the same transactions that one another have seen. They're just, because the network is so large and is connected by so many nodes, in general, you can see different miners mining different blocks. In this case, I've illustrated them as totally different. They'd probably be about the same, but
okay.
Different in the picture. So pictured here is the network. It's a small network. It's got 5 miners. And suppose that the miner in the top left in the U.S. were to strike proof of work at the same time.
Could be Canada.
Could be Canada.
Could be Mexico.
Right. Could be Mexico.
Wow.
And then in the bottom right, I'm going to say Australia. Sorry to New Zealanders. They also strike proof of work at about the same time, usually within, 30 seconds of one another. So they strike proof of work at about the same time. And then what happens is they both broadcast their valid proof of work. They broadcast the nonce, the header, and the contents of the block. And what ends up happening is that Asia and Africa see the Australian block, and then South America sees the North American block. What ends up happening?
Well, we end up with basically a split network where we have two different blockchains that continue to be mined and new transactions are added on. So that's what you can see here. We kind of have history splitting off. And we have this version in green that continues on, and people or miners are trying to find proof of work. Then we have this pink/purple magenta version down here where miners are trying to find valid proof of work. And remember, it all matters what the previous hash was because that is hashed in to the next block. So if there was another block after this one, so this one is mined and there's another block afterwards, it depends on that, and so on. And so what happens here is that one of these is going to be abandoned eventually. And it usually happens pretty quickly because, as we've already discussed, it's really not a good situation to be in, to be a miner mining a shorter blockchain. If there's another blockchain that's longer, that means that it's safer, it's more secure. Yeah, it's more secure.
People are more inclined to participate on a longer blockchain that has more work applied to it because it means the earlier transactions are hashed under more actual power of proof of work. Yeah, and that means they're more secure.
So in this case,
they're harder to undo.
If these two are neck and neck, and they're both working trying to find proof of work, two parts of the network split, trying to find the next valid proof of work. So in the last slide, we deliberately showed a split here where the pink side has more miners involved because it's more likely that they're then going to find proof of work faster, that they're going to pull ahead. It's not impossible that green could, but in our situation, it's more likely. So in this case, pink pulls ahead, finds a valid proof of work, cementing the next block, which green was still looking to find. So pretty much everybody on green is going to just abandon that and say,
as soon as they hear about it,
we need to join this new block. And basically this is truth now. This is history. Ignore everything we were just working on because it's worthless at this point. So it's abandoned. Hence the orphan block. That's the official terminology. And what we'll do now is actually show you some instances in history when this happened.
Yeah, and it's also important to note that the abandoned blockchain, this cool dude smile, North American block, anyone who earned Bitcoin, the actual miner who earned Bitcoin for mining that block, does not actually get that Bitcoin because that transaction isn't included in the new main chain.
So much hard work gone. So here's a webpage that shows us a history of orphan blocks. Their little definition: detached or orphan blocks are valid blocks which are not part of the main chain. So they are valid. That's the important part. But this occurs naturally, as you can see here, when two miners produce blocks at similar times.
And they also note that this could be caused by an attacker with enough hashing power who is trying to reverse transactions from the main chain. In general, that's computationally untenable right now. It could be possible in the future given centralization, but in general, you don't have to worry about that.
Okay, so what you can see here, it looks like the last one of these orphaned blocks or the detached blocks was back in January of 2018. And this was the blockchain when it was basically one blockchain. And there was no disagreement. This was block, 503,948. And at one point, there were two valid proofs of work found. So both of these were called block 5. They had height of 503,949. They came directly after this because two different miners found proof of work. And they were, the same day, 23/28/07, 23/28/33.
Yeah, so 26 seconds apart.
26 seconds between them. So they found it too close to one another, and it propagated across the network. They both propagated across the network, and two different parts of the network started mining.
So it's also important to note that relayed by is listed here. And relayed by refers to the actual party that mined the block. And in this case, it was two mining pools. A mining pool is a team of miners that team up to spread out the risk. And by participating on a big team, you contribute an amount of effort and you also get part of the earnings of the entire group. So what probably happened is Slush Pool propagated their valid block within their network within 26 seconds of GB miners having found their proof of work. The GB miners found theirs or heard theirs first, and the Slush Pool heard theirs first, and they both continued forward.
And then eventually proof of work was found on this block and not this block, it looks like. And so then this one was abandoned and people moved on to block 503 950. I don't know why I said it that way. 503,950. The next block. And this was left and abandoned. So whoever found proof of work over here didn't actually get paid at all. It's very sad. They had to abandon everything, give up, and start on this chain over here. And you can see if we go back, there's a bunch of these, but overall, compared to the number of blocks, it's really infrequent.
Yeah,
so
it's like once a month in the last year.
It looks like, so January 12th, then December 6th. This tends to happen or coincide with times of increased latency in the network, meaning that there's longer periods. It takes longer for people or miners to communicate with one another, to let each other know what's going on. And that usually coincides with higher traffic on the network.
Oh, look, slush pool lost again.
Yeah. So yeah, you can see this. Let's see. There was November, October, August. Yeah, it looks roughly, I'd say, once a month or so, at least over the last year. Anyway, that's the idea of an orphan block. 2 proofs of work found. Only 1 blockchain wins. All right, now that we've learned more about mining, we've talked about Hashcash, we're going to talk about how this all works together to make Bitcoin more secure and more tamper resistant. And we've already touched on this, but we just want to go into more detail now that we understand what mining actually is, what the operation or the trillions of, quadrillions? Quintillions of operations,
Sextillions.
Whatever, the huge number of operations that are happening. We understand why that's hard. Now let's talk about why that makes it difficult for somebody to change something in the past, to tamper with the ledger.
So pictured here is the head of the blockchain. And on the far right, with the circular arrows, we've indicated that someone, actually the whole network, is working on finding proof of work, finding, in this case, a yellow emoji. So for a lot of these examples, we're going back to our emoji example, so we don't have to look at the little tiny hex values. Let's just think about finding a yellow emoji. So the previous values are all authentic or all valid, and now we're working on finding a yellow emoji for this block. So for somebody to break in and tamper with, for example, the leftmost value, suppose we want to add this little red transaction.
With the skull.
Yeah. So if we wanted to change that light blue transaction to the red transaction, what we would have effectively done is change the fingerprint of that block. And now the new fingerprint is very likely to not be a valid in terms of proof of work.
Right.
It's probably not less than the target.
Yeah, and that's, we're adding this transaction. We haven't done anything. The nonce is the same. Remember, this was the nonce 53 that was found to result in this yellow emoji with the blue transaction there. But when we swap out the data, we're still using that same nonce. We haven't tried again to mine this. So we're going to end up with a different fingerprint. In this case, what is this, an owl?
Little owl. So all things left constant, we change one little value, and voila, now we no longer
Kevin loves
have...
to say voila.
Voila. Now we no longer have valid proof of work for this block. The nonce doesn't work. Now, for a client to the Bitcoin network, they would see this block, and they would say, this looks wrong. I'm not even going to take this one seriously. Clients want to see that given a nonce, given the transactions, and given the block header, that we have a valid proof of work, that the output starts with, give or take, 20 zeros.
Yeah, it's less than the target.
So the person who on the bottom has now tampered with it, who's indicated with this little red skull, would then want to catch up to the authentic blockchain. So the owl fingerprint has changed, which means if we want to propagate that outwards, if we want to make the actual chain, then in the next block, we'd need to update the previous fingerprint. So we'd change that previous fingerprint to the owl, and now the next block, this one in the bottom middle, is a watermelon, also not a yellow emoji, given the same nonce, given the same values. So this watermelon brought out to this third block on the far right is now referencing, the third block is now referencing a previous emoji that's not even yellow. So what do we want to do if we want to actually take over the network and add our red malicious transaction? We'd have to start at this leftmost value, or at this leftmost block, and find proof of work on it. Now, proof of work, as we continue to dwell on, is really difficult to do for especially any one individual. So the whole network, it takes about 10 minutes. Suppose you're just one person, and suppose you're even a very prolific miner and you have 10% of the mining power of the network. Even with 10% of the mining power of the network, to catch up all the way to where the current network is, you would have to start hashing as fast, if not faster than them. Because remember, it's the blockchain that is taken the most seriously, that is considered the most valuable, is the longest one. So we'd start at the left, we'd begin mining proof of work, but remember, the rest of the network, the other 90%, are working on the authentic chain. So the likelihood that we catch up, even from 3 blocks back, is so infinitely small that the rest of the network doesn't really take this 10% of defectors seriously. It just falls behind, and it ultimately becomes irrelevant.
Okay, so returning to this blockchain demo, we have our same transactions. We have 5 blocks. Currently, everything has been mined. It's all green. There's nonces. There's valid hashes. Everything works. But what I'm going to show is if we change one of these, we've already seen this, but we're going to show what happens when we remine. So first, I'm actually going to take, let's go to the beginning here. I'm going to take a screenshot just of these last 2 blocks so we can reference them. Now what I'm going to do is let's go here and say there's some malicious actor who wants to change this to be 210 Bitcoin. Okay, so now this block is messed up because we no longer have a valid proof of work. Remember that we're trying to start off in this example because it's all done in JavaScript in the browser. We're not talking about 20 zeros at the beginning, which would take potentially years for this computer to do. Or what did we say, a year?
I think 10 million years for a laptop.
Way off.
Yeah.
So instead it just does 4 zeros at the beginning. Anyway, what I would have to do is the rest of the network is still up here, moving on to the next block. Everybody has, as Kevin has already mentioned, as soon as somebody finds proof of work, everyone abandons what they were doing and joins on that solution and keeps going and adds on to it. So here what I'm going to do is click the mine button. This is not actually what mining looks like. You don't click anything really, but you'll see it takes a little bit. The nonce is going to change.
Spinning, spinning, spinning.
Here's the new nonce, and this hash that was found has 4 zeros at the beginning. Okay, so now this block needs to be updated because the previous hash has changed to be 0000F, but we need to find a new nonce. We need to use that. We need to fingerprint all of this together, including the new value of that previous hash. This has to be in there, and this is going to change the output, so let's mine it.
And hurry, 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 because the rest of the network is still continuing forward. We're trying to catch up. So if you were to take over, for example, just 10% of the network, which is a lot of the network, it's 1,000 full nodes, then your 10% mining power against the rest of the network, if the full network is taking 10 minutes to find proof of work, your 10% would probably take about 100 minutes to find proof of work on just one block. Meanwhile, the other 90% are continuing forward.
Well, and there's one other thing to discuss. So let's just finish this. So we have a new hash down here, a new nonce. So then it's been updated here. The previous hash now reflects this one. So we have to remine this block, find a new nonce so that our end result, the fingerprint of this entire block, has 4 leading zeros. Here we go. Kill some time here. All right, so that finished. I'm now going to take a screenshot again. Okay, so here are the 2 screenshots now of just the final 2 blocks. Let's just say that magically you were the luckiest person in the world. You managed to find proof of work, not just once, but twice or 3 times in the time that the rest of the network were able to find one proof of work.
Yeah, your 10% caught up to the rest of the network.
Which is like insanely unlikely.
It's very unlikely, yeah.
But let's just look at the results there. I don't remember which one is which. One of these is the first version, the other one's the second version. It doesn't matter, but if we look, the transactions, in this case, the transaction's the same. But if we look at the hashes, they're totally different. The nonces are totally different. So you're not trying to find the same data, right? There's many solutions to a given proof of work. It's just that it's so hard to find. It's a needle in a haystack, but there's still, I don't know, thousands of needles in that haystack.
Yeah, I wouldn't want to be climbing
massive,
around in that haystack.
Yeah. So you're trying to find, a viable solution. And so what we have here are 2 blockchains now that are actually valid. As far as if we look at them from a security point of view, they are fully mined. Proof of work has been found for everything.
So in this scenario where you have caught up with your 10%, what miners are automatically going to do is they're going to prefer the longest valid blockchain. So if your 10% were to actually pull ahead right here, then the rest of the network would actually see this and see, hey, there's a valid blockchain. It's length 5 or it's length 6 now. And even though we're the 90% and it looks like most of the network is working on one chain, we're only length 5. What that means to the mining software is let's go with the more secure option. The blockchain with 6 blocks is technically more valuable or is heuristically more valuable because it's more secure. All the transactions in it have had more cryptographic work piled on top of it, which means that people will want to pursue that. So if you did manage to pull away, you would have successfully taken over the network not really taken over the network, but inserted your invalid transaction, your false transaction, and then the network would believe it.
So anyways, what we're trying to show here is that as you go further back in time into the blockchain, you alter something, the amount of work that you would have to do to try and convince everybody that it was valid grows, and it continues to grow. And remember how much time it takes just to find one proof of work. If you're trying to do something 1,000 blocks or 10,000 blocks ago, that's going to be insane. And I mean, maybe once we have quantum computing or something, that would be possible to do it fast enough to catch up to everybody. But otherwise, it's infeasible. So as time grows, the power or the security grows. As future blocks are cemented and laid down, it becomes harder and harder to tamper with the past.
Exactly. Yeah, that's why miners prefer a longer chain. You can create a brand new blockchain and do a really low difficulty and put some transactions in it, but people won't really want to spend assets stored on that chain because they won't be confident that those assets can't be manipulated. People believe in Bitcoin, which is something we've been really aiming towards explaining. People believe in Bitcoin because cryptographically, they've threaded the needle so many times. They've threaded the needle 520,000 times, which makes it inherently valuable.
All right, welcome back. So we've been talking at length about blocks and the blockchain. What we're going to do now is introduce an exploit that takes advantage of the 10 or so minutes that it takes for a block to be hashed. And it's called a double spend. But first, let's just illustrate it. Suppose I'm selling a car on Craigslist or something like that, and for some reason, I only want to accept Bitcoin. So it's going to be a large amount of Bitcoin. Well, I guess with today's prices, it's probably like 1 or 2 Bitcoin.
I'm going to buy your car for 2 Bitcoin.
Okay. So I post this ad, Kevin responds, he comes over to pick up the car, and I've never sold anything for Bitcoin before. So he tells me to download an app, I do it, he scans my address, he shows me that he's hitting send, and it hits my address, on my wallet app it says, all right, here's a new transaction, pending, blah, 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 you can see this amount to Bitcoin from this address, and I give him the keys, and he drives away.
And it's important to note that it's still pending, and then I drive away.
Yeah. So then a day later or so, I go and check and try and cash it out or spend it on something else. And I realize that I don't have that Bitcoin. What happened?
What did I do?
It's a double spend.
Well, what I did was in the background, created an extra address. And this also works. It improves my odds if I create a bunch of addresses. But right now, we're going to talk about one malicious address and one of Colt's address. So in this case, what I did is at the same time as sending that transaction to Colt, also created a transaction with the same source, with the same existing Bitcoin, and sent it to both Colt's address. So he got the confirmation, or he got the notification saying, oh, incoming Bitcoin transaction. But I also sent it to an address that I own. And this is a problem with digital currency. This is the difference between something digital and a physical commodity, is you can trivially duplicate it.
Right. Well, and why is this really a problem, though? Because if this one went first, even by a millisecond or a fraction of a second, shouldn't it just be added in first, Kevin?
Well, so I can change the timestamp on my transaction, and I can tell the network, hey, I actually created this transaction 10 seconds ago, 10 seconds before the transaction destined for Colt. Now, some of the miners and Colt's wallet app might indicate that, might only see the transaction destined for Colt. And in that case, it would say, okay, incoming transaction. So let's illustrate this in pictures. On the top, to the destination, this is the Bitcoin transaction destined for Colt. And on the bottom is the Bitcoin transaction destined to my own address.
Evil.
Now, so red is evil, blue is good.
Yeah.
Now, in the next slide, we'll show what they look like on the actual blockchain. Here they are on a block. And in this case, the red transaction appears before the blue transaction.
The evil one.
The evil transaction appears first.
In which case, miners are going to reject the blue one because they're going to realize, wait a minute, this address had, let's say that Kevin had exactly 2 Bitcoin in the address he was sending. The miners will notice that that address that Kevin sent the Bitcoin from had already been spent. The 2 Bitcoin had been moved to another one of Kevin's addresses. The network has no way of knowing what's real and what's not. It's just a to address and a from address and an amount. And so if it received this one first, it's going to assume that mine is fraud, or that's maybe we shouldn't prescribe intent to it. It's just going to reject it because there's no Bitcoin to be spent. That address is gone. So it doesn't get added to the blockchain. So even though I got a confirmation, well, I didn't get a confirmation. I got a notification from my wallet app saying, hey, we noticed there's a transaction. It's pending. Wait for confirmations. If I don't wait for those confirmations, which means that it gets hashed into a block over and over and over, if I don't do that, there's a chance that Kevin could have double spent.
Yeah, this is not a guarantee, but it is a vulnerability because it's a possibility. And if I'm buying something, for example, 2 Bitcoin, and I'm a real jerk, then hey, that's great odds. I'll take a 50% chance of getting a free car.
Yeah, so all you want to do, honestly, is just wait to make sure that you get those confirmations. If you're selling something for Bitcoin, it's not really, it doesn't really make sense as a quick turnaround currency, as something you would buy coffee with, for example. Buying a car, though, you could have Kevin send the currency ahead of time, or I could just have him wait 30 minutes or so to get a couple confirmations.
So let's look at this on the actual on a split blockchain. So suppose we have miners looking at their own versions of blocks. On the top, we have the transaction destined for Colt, and on the bottom, we have the transaction destined for me. Both of them exist at the same time, just in different miners.
Mm-hmm. So let's say roughly half the miners have the transaction to me, the good one, and half of them have the evil one, and it's just a matter of which one they found out about first. That's the one that gets hashed in. So what would actually happen, just like any other disagreement that we've talked about, the longer chain is going to win. So whoever finds proof of work first, which in our example, let's say that unfortunately a miner finds proof of work for the evil chain. Well, the chain isn't evil, but it contains our evil transaction down here. Then the miners that were working on this block are going to abandon it and come join this side, meaning that the transaction I thought that was sent to me, that my phone told me about, even though it never said it was confirmed, I at least saw that it was going to be confirmed, or so I thought. Well, that's gone, and I just gave away my car.
Now, this is hard to pull off.
Yes.
Just because normal wallet apps aren't going to let you do it. But you can build your own wallet app. All it takes is adherence to the Bitcoin rules, and you can interface with the network. And because of that, it's important to know that this is a possibility, and it's important that we show you this because this is the reason for a lot of the latency in Bitcoin transactions. Is many of the services and many of the individuals using Bitcoin are going to insist on waiting for block confirmations. And that has the effect of slowing the actual process down in exchange for more security.
Right. So we're not saying this to scare you that it's something you have to constantly be worried about, but it's more just it helps explain why you need to wait a little bit for your transaction to be officially confirmed. And also, this is one of the reasons that other cryptocurrencies, it's one of the problems with Bitcoin, I guess, that other cryptocurrencies have attempted to address. Things like Ethereum, we'll talk about later, have a much faster time for a block, so that if you want to wait for a couple blocks to be hashed, it might only take a minute to get 3 or 4 blocks rather than 30 minutes. All right, welcome back. So what we're going to do now is address something that we've kind of been avoiding a little bit. We've mentioned the fact that there are fees associated with Bitcoin transactions, but we haven't really talked about where they come from, how they're decided, and what they indicate. What's the point of them? So that's what we're going to do now. Basically, we've learned how transactions work. There's just one missing piece, which is the fee. But first, we got to talk about block size.
So this is a fictional block measured in generic units. A real block is measured in bytes. But for this picture, before we talk about the real size, we're just going to use this for fractions. So This is a 100 unit block. And in a perfect world, a transaction would just be exactly a neat 25 units. You could fit 4 transaction, nice and neat, no extra space.
Or why not like 1 unit?
1 unit would even be
and then we could have 100 of them.
But we need to have some information. The source address, the destination address, the signature. In reality, what ends up happening is transactions are not all the same sizes. So let's cut to the blockchain to see why that is.
All right, so I'm here on the Blockchain Explorer again. This is block 520,832. And if we look here, just as I scroll down, some of these transactions are all pretty different. Obviously, they have different addresses and amounts. But look at how many addresses this one has as inputs. 3 addresses, and then 1 address that it's being sent to. Or this one has, 5 of them?
Yeah, so that transaction, for example, the 5 to 1, means that this person put 5 separate addresses worth of Bitcoin and sent them to 1 address.
Yeah.
And that's 5 input components and 1 output component. And each of those is represented on the blockchain or in a block as bytes.
It looks like they were consolidating into a new address that had everything from before. Before we go back to the slides, I just want you to see that there are transactions of all different sizes. 1-to-1, we have 2 inputs to 2 outputs, or we have, what do we have here? 3 inputs, 1. Anyway, they're all different sizes, and so they don't take up the same amount of space.
So back to our fictional blockchain or fictional block. Now we have a real block. So in this square, we're representing 1,000 bytes as just this rectangle. So
that's not a block.
This is not a block. Actually, 1 block is going to be 1,000 of these squares. Actually, 1,000 and a tiny bit more for those of you who are very detail oriented.
But it's 1,048,000 bytes roughly?
1,048,576 in a megabyte.
So anyway, what we have here is just a small representation, but the smallest possible transaction, a 1 address to 1 other address, takes up 191 bytes.
Yeah. A 1 in and a 2 out, which is a little bit more common, actually a lot more common, is going to be 250 bytes.
Okay.
So this variance means that the number of transactions that fit in a block varies all the time, and that's why we haven't given you a hard number. We say about 2,000, about 2,400, and that's because it really depends on the constituent transactions. So now let's look at scale. So in this window, these are drawn to scale. If the entire window that you're looking at this in, assuming you're looking at 1080p or 720p aspect ratio, actually, regardless of aspect ratio, that square, the pink one, would be about the size of an average transaction. The green one would be a bigger transaction. And this is about how much room in a block you have to fit. So
all this space here.
Yeah, so every 10 minutes, the Bitcoin network can handle this much space worth of transactions. And this is where the controversy comes in.
Right.
A lot of people want to make this space bigger. A lot of people want to cut down the size of those squares. You can actually segregate part of the information in that square to somewhere else. It's not that important to the average Bitcoin user, but just know that there's a lot of controversy around the impact on the size of a block and the scale of what Bitcoin can handle. If they ever want to become a high-speed payment network, they're going to need to be able to handle more transactions than they do every 10 minutes right now.
Yeah, and it also really only matters because there's so many people, so many transactions trying to be made at a given point. If we're talking about 10 transactions a day, the block size doesn't really matter.
So this slide shows 100 tiles, each of which represents about 1,000 bytes. It's actually, 1,048,576 bytes.
This is the size of the block. Anyway, we've changed the scale now down to here.
Now we're at grid scale. Each square represents 1,000 bytes. So the biggest transaction ever was actually 999 kilobytes. And this is just a massive transaction because of the number of inputs and the number of outputs. In that case, the block held 1 transaction.
Okay, so we've talked about this idea of a finite block size that currently is set and may change eventually, but it hasn't. And we've explained the problem of transactions not all being the same size, so they don't just fit neatly in there in a little box. Sometimes they're a lot larger than others. So there needs to be a way to incentivize miners to take on certain transactions.
Yeah, so set priority.
Yeah, and that's where fees come in.
Enter fees, people's favorite part of Bitcoin.
Yeah.
So fees are set by the transaction sender, and the miners get the fees of any block. When a miner strikes a block, they get all of the fees associated with every transaction in that block. And what's that mean? That means that miners are incentivized to include the transactions that have the greatest fees.
So it just means that if you have a really high priority transaction you need done as soon as possible.
Like you need your coffee right away.
Yeah, well, you probably don't want to use Bitcoin
like
for that
10
anyway.
minutes right
but if
away.
you did want to make sure it's as soon as possible, you would pay a higher fee to ensure that.
Now, what's that mean about network congestion? So when the network is congested, which at times it definitely is, you can't fit enough transactions into a single block. This begins a bidding process, and it's not really a dynamic bidding process. It's just whoever is trying to create transactions will look at the network traffic and see, the network looks congested. I'm going to bid higher. I'm going to pay more, a greater fee, which will hopefully get me to the front of the queue. And miners select for the greatest fees. If your transaction doesn't make it into the current block, it's not that big of a deal. The miners all have a queue and are going to get to it eventually. But this is where the latency of a Bitcoin transaction comes in. If you need your transaction immediately, you got to bid higher. If it doesn't matter when it clears, then you can bid quite low.
Yeah. So we'll wrap this up by showing a history of Bitcoin fees, and you can see that they have fluctuated quite a bit. And this spike here at one point, let's see, the average transaction fee was $32.
Oh no, it got higher. That's not even the peak.
Is it? Oh, you're right.
You're
right.
50s.
I thought there we go. 55.
Yeah, this is the average transaction fee. So what people are paying in general at the spike.
And this was back in late December of 2017.
Yeah,
there was
Christmas
a
time.
huge spike in interest and activity on the Bitcoin network, and that coincided with a lot of traffic, a lot of transactions, higher fees. So $55 is pretty high because that doesn't change with the size of the transaction. So you could be paying $55 for a $100,000 transaction, or you could be paying $55 for a 50-cent transaction.
Yeah, which hopefully you're not doing. But
Yeah.
what this means, this is useful for some people. If you need to transfer $100 million, you probably want to break it up into a few, but you don't have to pay some massive clearing fee.
Lastly, this is something that a lot of people criticize Bitcoin for, and other cryptocurrencies try and fix or build upon, have lower fee structures or different fee structures, and also try and avoid the problem of too small of a block and overloading the network and having a queue and all of that. There are other approaches that ensuing cryptocurrencies have attempted.